In the first robot arm tutorial, I showed you how to set up your simulation using hard-coded values to make the arm move over, pick up a ball, and then drop it into a bin. In the second tutorial, I showed you how to hook that simulation up to control the real robot and produce very similar behavior without having to write any code for either your master microcomputer or your embedded microcontroller using the Fermata I/O controller. That version used only velocity control to move the arm. In this tutorial, I will show you how you can easily swap out that original I/O controller for a completely different one, the USB to Dynamixel controller. In addition, I'll also demonstrate how you can control both the position and the velocity of your servos using AnimatLab instead of just relying on velocity control. This method of controlling your servos is more accurate and gives you much more power to control what actually happens with your servos. We'll begin building this tutorial with the project from the end of the second tutorial, where we had the Fermata I/O controller on the real robot moving our arm to pick up the ball and drop it in the bin. If you'd like to just skip over the first tutorials and start working on this one directly, you can do that by downloading the Fermata project from the AnimatLab warehouse. Go there and search for Robot Arm Control Base Simulation. This will allow you to follow along with this tutorial. We'll be swapping out our original Fermata controller for a USB to Dynamixel controller from Robotic. This is a small USB stick that uses the FTDI USB drivers to create a virtual COM port to your computer that you can then use to talk to your servos. Please note that this controller has some severe limitations compared to the Fermata that we used previously. The first is that you can only use this to control Dynamixel servos and read data from them. It has no capability to read any other type of input data like was possible with Fermata. Also, the Robotics Fermata system is much faster than the USB to Dynamixel. On a Windows system, the fastest I was able to get it to read from a single motor was around 4 milliseconds. Whereas I was able to get Fermata to read all 3 of my servos and report this back to the master computer in around 1.5 milliseconds. And I believe I could handle more than 3 and still not bump that time up too much. But I've not had time to fully test this, while the USB to Dynamixel seems to require around 4 to 5 milliseconds for every new servo that you add. I'm not completely sure why it's so much slower. There are some settings I'll discuss that Robotic recommends to get faster speeds, and I've set those, which is good because it was even slower before I did that. However, this has serious consequences for our control loop. If you're doing only feed-forward control, it may not be that big of a deal. Sending commands to the servos is pretty fast, and it takes much less than 5 milliseconds to send out a synchronous command to set the position and speed of all the motors. So you can still get around 200 Hz update rate. However, if you want to use any feedback or get any data back, then the time it will take to get data back from all of your motors will be around 5 milliseconds times the total number of servos. As you start adding more servos into your system, this really begins to bite. For example, for a hexapod walking robot, we typically have 18 servos. That would be a total read time of 90 milliseconds. Rounding that up to 100 milliseconds, that would mean we would only get back data on all our motors about 10 times a second. This will make it very difficult to actually use that feedback data to control a fast-moving robot. Take an example where we want to monitor when a leg reaches its posterior extreme position. In a feedback system, you'd want to monitor the leg position, and when it went past a certain angle, use this, along with some other sensory information, to switch the leg to begin its swing phase to move back for the next step. If the leg is moving fast enough and we get back our sensory data slowly, then what happens is that the leg will blow past this test position and reach its maximum value and stop there until the next time the sensor update happens, and this will cause jerky, uncoordinated movements. If you do decide to use this I/O controller, please be aware of these issues and plan accordingly. When I began building the controller for this system, I didn't realize it would be so much slower than the other system, or I would have just dropped it and concentrated on Fermata. However, it's built now, and even though I don't plan to use it for any of my future robotic systems, it is available for others if they want to use. The main purposes for this tutorial are to show you how easy it is to swap out your controller with a different one, but most of all to show you how to use position and velocity control for your Dynamixel servos. Let's start by getting the simulation set up. Then I'll discuss how the hardware is hooked up. We'll begin by just replacing the current velocity control of the servo motors with the USB to Dynamixel controller. Once we have that working, we'll switch it over to use both position and velocity control to see the difference. Let's begin by removing the Robotic controller from our existing system. Then we'll add a new I/O control and choose the Dynamixel USB controller. This controller is similar to the others in that you have a COM port. The difference is that you just specify the port number here. For my computer, I'll be using port 5. You'll need to change this to match the value for your own system though. Next is the baud rate. This is specified differently than on the other systems where you've been using. The Dynamixel USB SDK uses an integer setting for this. 1 is the fastest setting, and I would leave it defaulted to this. Now let's add a new hinge control. Change the name to be TC. We'll leave the servo ID as 1 and set the link part to be TC. We'll keep query motor data set to true so that we can get back data on the position and velocity of our motor. Also, we want all our servos to reset back to their start position at the beginning of each simulation. So let's set reset the start position to true as well. Now add another hinge servo and name it CF. Set its servo ID to be 2, linked part to be CF, and reset the start position to be true. Next, add a prismatic servo. We'll name it L gripper. Set its servo ID to be 3, link part to be L gripper, and reset the start position to true. Then set the translation range to be 2.3 centimeters. Finally, because of the issues with the update rate for the servos, I've added a new feature for these servo parts to try and reduce this problem. This is the update queue index. If this is set to -1 on a servo, then it will read in the data for that servo every time the I/O runs its update loop. However, if you set this to other positive values, you can have the servos do updates in a round-robin fashion. For example, let's set the TC servo to have a queue index of 0, CF to be 1, and L gripper to be 2. Now, the first time the I/O updates, it will pull the data only from the TC joint. On the next update loop, it will pull it from the CF joint, and on the third step, it will pull it from the gripper. If you wanted to have multiple servos pull their data on the same step, then you need to set them to have the same index. For instance, if we had TC and CF set to 0 and gripper set to 1, then it would pull the data for those two joints on the first I/O step and the gripper on the next. This doesn't change the overall update time needed to get the data from all the servos. For 3 servos, this will still be around 15 milliseconds. However, what it does do is let us keep the overall robot time step lower. If we didn't have this ability, then we would need to set the robot time step on the interface to be 15 milliseconds to match our feedback loop. This would slow down our ability to send out motor commands to our servos. By using a round-robin approach, we can instead set our robot time step to be about 5 milliseconds to match the time it takes to read a single servo, with a little extra time to send out our motor command. Since we changed our robot time step, we should go back to our adapters and change their sync update interval to match this new value. And that's all you have to do to swap in a new I/O controller for your servos in the simulation. Pretty easy, huh? Let's run the simulation again just to make sure it still works okay and to get a clean set of data. But before we do that, let's change the collect time interval of our chart to be 2.5 milliseconds, so the chart data from the simulation will have the same time base as what's collected in the real robot run. Since we moved the robot time step to 5 milliseconds, then the neurons in the chart have the smallest time step at 2.5 milliseconds. so the chart will use that in the real robot. That looks good. Let's go ahead and export out the data and then append _sim onto the end of the data file to save it for later. Now let's look a little at our new hardware and actually test this on our computer. The USB to Dynamixel actually needs another component to power the servos. This is a small 6-port power hub. The USB to Dynamixel only generates the control signals for the servo. They need to be powered from a different supply. The USB to Dynamixel connects to your computer and then it connects to the hub, and the hub has the power supply for the servos connected to it. Also, please be aware that there are some configuration issues you'll need to perform to get the USB to Dynamixel to work. The first is that you need to use a special version of the FTDI drivers to get it to run. I put a link to the documentation for this on the webpage for this video. Please use the standard Robotic tools to ensure that your USB to Dynamixel is working before attempting to run this using AnimatLab. Finally, you also need to change the settings on the COM port in order to get faster data transfer speeds. I'll also place a link to this documentation on the website for the video. Once you have those things configured and you have the USB to Dynamixel connected to your computer and the robot's powered up, then we can try and use it to control our robot. Let's export out a new robot simulation. And then run it. Good, that looks essentially the same. Let's go ahead and open up the data and compare the simulation and real data. And that looks pretty good. You can really notice the larger time steps that we have to use for the motor updates now. And that's going to increase the error between our real system and the simulation. But otherwise it looks pretty close. Now let's switch our network to control both the position and the velocity of the servos. Let's start by renaming the CF and TC neurons to be CF position and TF position. We'll change these neurons so that they control the position of the servos. Now let's change the two servos to use position and velocity control by setting the motor type. Now go back and select the TC adapter. When you open up the choices for the target data type, you now see both position and velocity listed. Let's choose position. Let's do the same thing for the CF adapter. And then try and run our simulation again. Now those joints and the arms don't move at all. The reason for this is that we're now setting their positions using our neural firing rates, but we're never setting their velocity, so it stays 0 and they never move. So let's go ahead and fix this. Copy the grip open neuron and paste it twice. Let's call this one TC-vel and this one CF-vel. Then draw connections to the corresponding joints. Set the new adapters to have a 100 millisecond delay in simulation. And a sync update interval of 5 milliseconds. Now let's modify the position adapters so we can set the full range of motion for them. We currently have our hinge servos set up with limits between positive and negative 90 degrees. So let's change the C parameter to be pi at 3.141 and the D parameter to be negative pi over 2 or negative 1.57. Now when our neuron is at its half activation state, it will correspond to a position of 0 degrees. At full activation, it will correspond to pi over 2 degrees, and with no activation, it will be negative pi over 2 degrees. Now do the same thing for the CF adapter gain. We'll leave the gains for the adapters of the velocity neurons at their default value of 1. One thing to keep in mind when using both position and velocity is that the velocity setting should always be positive. You'll set a goal position and then a goal position velocity to achieve that position. So let's add some stimulation to the new velocity neurons to make them go. Let's just set them to be always on. And we'll keep the current of 10 nanoamps so they move at 1 radian per second as they did before. Finally, now that we're using position control, we need to modify some of the original stimuli as well. First, let's disable the CF up and TC return stimuli. We no longer need these now because we'll command our servos to move to a specific position for a period of time and when our stimulus expires, they will automatically go back to their 0 position. To try and get the same behavior as before, we'll need to change the end times of the CF down and TC over to be the start times of the CF up and TC return. Finally, we only want our arm to go down just a little bit, so let's change the current for the CF down stimulus to be negative 0.64 nanoamps. This will command it to move down by a small amount and stay there for the duration of the stimulation. Let's go ahead and run our simulation. Okay, looks like I forgot. We need to change our target data type for these new adapters to be desired velocity. Let's try that again. There we go. Now we have the simulated arm moving over, picking up the ball and dropping it in the bin again, but this time using both velocity and position control. Let's export out our data and add _sim to it for later, and then let's export out the robot sim. Great, he was able to do it again. Let's go ahead now and compare the real and simulated data results. Now we can see that the error over time that we were getting with just velocity control is essentially gone. Using only velocity control, you'll gradually accumulate errors and they'll not get corrected. However, when you use both position and velocity control, you'll get small errors during the movement, so it may not reach the goal position at exactly the same time in the simulation as a real robot, but it will reach the goal position and basically start fresh on the next movement, so you don't accumulate errors over time. Next, let's change the velocity of our movement using neural control. Go ahead and disable all of the stimuli except TC over and TC velocity. We're going to just concentrate on it for now. Change the TC over end time to be 5 seconds. And then change the TC velocity current to be 3 nanoamps. Let's run the simulation again. This time we commanded the arm to move all the way over again, but we decreased the velocity stimulus and made it move much more slowly. We can also use this to do fine control over motor movements. Let's set our TC joint up to move in a sine wave. Make sure TC velocity current is set back to 10 nanoamps. For this example, we want the velocity to be maximum so it can respond quickly to changes in commanded position. Then we'll alter the frequency of the position to make it move slower or faster. To do this, go to the TC over stimulus and change it to use an equation. Set the end time to be 40 seconds and the current to be the equation -2 times sine of 1.5 times t. This will apply a sinusoidal current to our TC position neuron to make it move back and forth. In our chart, let's change the contact axis to instead be desired position. And then add the CF and TC joints and change their data types to be desired rotation. Finally, let's move the red block and ball out of the way. Add a 2 to the beginning of their Z position to get them out of the way. Now run the simulation again. We can see that the TC joint now tracks the sine wave we commanded for its movements. Let's export our chart and add _sim on the end of the file. Then export our robot simulation file. Great, that looks essentially the same. But let's check the data to be sure. Open up the robot data. First, let's compare the TC position against the desired TC position. We can see that it matches fairly closely. Now let's compare the simulated robot movement with the real one. And again, we can see that they match very closely. You can change the frequency of the movement by changing the period of the sine wave. Let's go back and set it to be 0.5 and then try again. This time I'm going to change the end time for our charts and for our simulation end time to be 20 seconds, so we'll be able to see more of this movement. So let's look again at the data. So as you can see, we were able to very closely match the simulated and real robot output for our slower sine wave. So this gives you the ability to make very fine movements. Another thing I'd like to point out is the ability to bias your movements. Let's add a new firing rate neuron to the network and name it Promote Bias. We'd like this neuron to generate a gradual increase in firing when stimulated, so let's set its capacitance to be 100 nanofarad. Then add an excitatory synapse to the TC position neuron and set it to 2 nanoamps. Then let's add a new tonic current stimulus to it. Set the name to be Promote Bias. Change the time to be from 9 to 19 seconds. Then let's change the data chart to record till 30 seconds and add our new neuron to it. Then change the sim in time to be 30.2 seconds and let's run the simulation. And actually, I forgot, we need to change our TC over period. Let's change it back to 1.5. Now we can see that the arm made its normal movements for the first 9 seconds, and then when our bias neuron was activated, it shifted the center of our oscillation. When it went off again, the oscillation shifted back to its original position. This will prove useful for more complex robots and movements. For instance, you could set a basic oscillatory circuit to produce leg movements for walking with the body held at a given postural position above the ground. You could then have different sets of command neurons that can be activated to alter that posture. So by just activating a raised command neuron, it can bias your walking pattern to raise the body up without causing any major disturbances in your walking pattern. Let's go ahead and export out this robot simulation and look at the real system. Now let's compare the data from the real and simulated system. Once again, we can see that our data from our real and simulated system match very closely. We can also see how our bias shifted up the center of oscillation, and then as that bias went away, it smoothly transitioned back into an oscillation around its original center point. Like I said, this is something that you could use as in a command neuron setting to actually just smoothly transition from one postural setting to the next. So in this tutorial, I've showed you how to easily switch out your I/O controller for a different one, and also how to use position and velocity motor control within AnimatLab to get very fine movement control of your robot.